Hello, my name is Timothy Hansen. I am representing the UMass Amherst UAV team. This is our entrant to the 2021 AIAA Design Build Fly competition. Our plane's name is Bad Attitude. This is our plane Bad Attitude and some of the team members before one of our test flights. First section is Airframe Design. The goal of this aircraft was to create a well-rounded, cargo-carrying, but fast aircraft that could perform well in all aspects of the competition. And on the right, you can see some of the headline figures, our wingspan, length, wing taper ratios, and our weight. Here's Bad Attitude in the flesh. Here's our propulsion systems layout. As I just mentioned, we were using a 15x8 prop. The prop size is given in diameter in inches. On the left, you can see a CAD drawing labeled with a few key points of our propulsion layout. Here is a detailed view of our cooling solutions for the propulsion system. As you can see, we have inlets for cooling the motor and also inlets for cooling the ESC, which is most important. We also have outlets on either side of the fuselage to allow the air to flow out from the ESC inlet. Here's a better view of it when you're looking straight down. Here's a control architecture. Our control surface layout, we have a few main control surfaces. We have ailerons, slotted flaps, elevators, and vertical stabilizers. We also had landing gear and throttles, so that took up all 6 of our channels on our RC receiver. As you can see, here's a labeled CAD view of where the servos and control horns are mounted. They're connected by a push rod. Servo arms comes out of the wing or the fuselage and actuates that pushes on the control horn that moves the servos. Here's a better view of the elevator. You can see the control horn and the servo coming out of the fuselage. Our ORC component layout was fairly simple. We had it all contained into one compartment area just after the battery storage. The receivers Velcroed in and then connected to the battery, which sat on the tray. The entire compartment was covered with a hatch that had an FPV camera mounted on it. Here's the mechanism RC. Now, the RC for the mechanism and the plane itself were on 2 different receiver and transmitter setups. The receiver for the mechanism was actually mounted after the wing box next to the mechanism RC, and it used the PWM outputs from the RC receiver that it got from the transmitter as inputs for the Arduino, and the Arduino had a code on it that would put outputs for the motor and for the lights on the sensor through the slip ring you can see attached to the mechanism on B, and then the servo door that would open and close during flight to allow the sensor to drop out. Now, our sensitivity study was a kind of key component of our design process. One key factor we really looked at was, 2 key factors we really looked at were the airfoil choice. So we used XFLR5 to find the coefficient of lift, critical angle of attack, and then in our MATLAB code, we varied our wing area. So as you can see right here in front of you is the combination of mission 2 and ground mission score. Now you can see as the number of containers increase, the ground mission score goes down drastically. However, the mission 2 score goes up until it levels off. That's the point where the mission 2 score does not become feasible anymore. So we actually concluded that number of sensor containers of 9, which would put the score about 1.55 on this graph. Now this graph is our wing area varied by number of containers and number of containers per time. Number of containers per time is a rough estimate of the lap time and the efficiency of the aircraft. So we went with a conservative estimate of 9 containers and a wing area of about 495. Now our performance predictions, as you can see here on the left, there's our payload. On the right, you can see the mission score breakdown. Now, our predicted performance was an estimated lap time about 27 seconds for mission 2. A total number of laps from mission 3 about 20. Average cruise speed was going to be about 71 miles an hour. Mission 3 score, without being normalized over the maximum for the competition, would be about 7.99. And the combination of mission 2 and ground mission would be about 1.123. unfortunately, during our most recent flight test, during the aircraft's climb out, the plane took far too hard of a bank. As such, we weren't able to capture footage of the aircraft deploying the sensor in flight. However, we do have the ground mission portion of that.